Okay, so for most of your time studying maths, you would have represented points in a 2D plane using Cartesian coordinates. And that is just when we take a plane, so an xy plane, a two-dimensional space. Okay, well, this is the x-axis, this is the y-axis, and a point P has coordinates x and y. X represents how far away it is this way from the origin, and y represents how much it is this way from the origin. Okay, so we go this across, this up, we find the point. Simple enough. But that is not the only way we can represent points in space, and for certain calculations it isn't the easiest way we can represent points in space. Okay, sometimes what we call coordinate transformations are quite useful. I'm not going to go too into that for now, but what we are going to talk about is one specific example which you need for the course, which is what we call polar coordinates. So in polar coordinates we define an origin, but we don't draw an xy plane. Instead we draw something called a half line, and all this is for is to help us figure out angles. Okay, so now if we have a point P in space, P has coordinates r and theta, where r is the length of the line from the origin to the point, and theta is the angle that point makes with the half line. Okay, so if we were to, the question you might be asking, because I think this makes sense, that you can, instead of defining a point, instead of saying to get to point P you walk this many steps east and this many steps north, you say you turn at this angle and then you walk this much in the direction you're currently facing. Okay, so that's a reasonable explanation of a point in space. But how can we convert between them? So, because obviously this point P is the same point. Okay, we're trying to describe the same point in space, and this is a generic point P, but yeah. So how can we convert between them? So let's take x to be the half line, because we can do that, the origin, and let's draw on this r and theta. Bear in mind this is x here, so this distance here is x, and this distance here is y. Okay, so y is here, so x is this distance here. Okay, we can use, bear in mind this is a right angle triangle, we can use trigonometry to start converting between these forms. So cos of the adjacent over the hypotenuse, cos theta is equal to the adjacent over the hypotenuse, that's equal to x over r, and that implies that x is equal to r cos theta, and sine theta is equal to the opposite over the hypotenuse, so that's y over r, and that implies y is equal to r sine theta. Okay, so that means if we're given r and theta to represent a point in space, we can find its Cartesian coordinates. We can find x and y using these formulas. Okay, so these help us with polar to Cartesian. So how do we go from the Cartesian coordinates into the polar coordinates? Well, if we look at Pythagoras' theorem, we can see that x squared plus y squared is equal to r squared, and that implies that r is equal to the square root of x squared plus y squared, and that's the positive square root, because if we're talking about a distance r, we're talking positive, and we always go r in the positive direction. So even if we turn all the way over here, okay, on that angle, moving an r would be going this way. We never, because if you think this point here could actually be described as an angle all the way around here, and then with negative r, but that just gets confusing then, because there's too many ways to describe the same point, so we tend to take r positive. Okay, restrict r to positive. So that was the point of that little ramble, is that we take positive r here, and then if we divide y by x, we see that that's equivalent to r sine theta over r cos theta. These r's non-zero, so we can cancel, that's fine, and that's equal to tan theta. So y over x is equal to tan theta, and we can use that to solve for theta. So now we have equations for r and theta. This is Cartesian to polar. Okay, and in the next video on further maths, we're going to see the usefulness of this when we look at certain integrals that are much more easily performed when we convert to these polar coordinates, and we'll see how you can convert your general integration, because normally you'd be integrating with respect to x. Obviously you're going to have to integrate with either respect to theta or r, so you will see how you can convert between those, and there's just some nice formulas for that, so nothing too complicated. Thank you for watching this video. If you did find it a useful introduction to polar coordinates, please like the video, and as I say, come back for that next video on integration using polar coordinates. Thank you very much for watching, and I hope to see you in the next one.